So we've seen a good example of what this training data looks like to our own brains as a two-dimensional representation, but let's also try to get an intuitive feel of what it looks like to the input layer of our neural network. So down here we've written another function, and its job is to flatten everything, keep it all flattened, and create a 2D image that just shows on each row of the image what each actual number looks like to that input layer of training neurons. So remember, we're going to have 784 input neurons on our input layer there, corresponding to one of each of the pixels in each 28 by 28 image. So when we flatten these images out from 28 by 28 2D images into a flat array of 784 individual pixels, our training data ends up looking like this. All this function is doing is creating a new image. We start with the very first image on our training data set, flattened out to 784 pixels wide, and then all the way up to the 500th image, we will add another row to that image for each individual training data. So let's go ahead and run that. So what we're seeing here is each row corresponds to a number in our training data set. And as you can see, your brain cannot really make sense of that very easily, right? So what we're asking our neural network to do is even more, in some ways, challenging than what our brains does, because it doesn't have that 2D structure. All it has is these basically spotty pixels here that represent the digits 0 through 9. And believe it or not, this neural network can actually figure this out. So it will basically learn to read the digits 0 through 9 just based on these flattened representations of each numerical digit. So it's seeing these numbers, seeing in quotations in a very different way than you or I do with our own human brains, but it still works. So let's go ahead and start to put together the neural network itself. First, we need placeholders for the actual input images and for the labels on the outside. So we need to have placeholders that will contain the input values going into our neural network and the labels that come out at the other end. So we're going to set up a placeholder for the input images that contains 784 neurons across. And then on the other end, we have 10 going across, one for each category for the numbers 0 through 9. Go ahead and run that before we forget. And now we can start to actually put together some of the variables that we need. So we'll start to construct the topology of our network here. We're going to say that we're going to have a hidden layer inside our deep neural network that's 512 neurons across. So those 784 input neurons will go into a hidden layer of 512, which will in turn go to our output classification layer. Now, in order to set up these layers within TensorFlow at a low level, we need to actually set up the weights and biases associated with each layer. So at the input layer, we'll have variables defined for the weights and biases that we will learn over time. We'll initialize the biases to 0 and the weights to a random normal distribution. And we'll do the same thing for the hidden layer. We'll set aside variables to store the weights and biases for those as well. And since these are variables, they're going to be maintained between each run of training our neural network. So we can actually use gradient descent to learn what these weights and biases should be over time. These variables are where that data will be stored. Okay, now we can actually start to set up the neural network's topology itself. We'll define an input layer. And again, remember that neural networks can just be modeled as matrix multiplications and additions by and large. So TensorFlow at its lowest level doesn't really know about neural networks. It just knows about matrix operations. And that's all we need here to get started. So our input layer will just be a matrix multiplication of the input image signal with the input weights. So the input images will be those 784 input neurons multiplied by the weights that we've learned to apply to those. We'll also set up our hidden layer, which will apply the ReLU activation function to that input layer plus the bias terms for the input layer that we've defined and learned over time. And finally, on the output layer, we will define the digit weights, our final output layer, as doing a matrix multiplication between that hidden layer and its learned weights over time, plus the learned biases of that hidden layer. So that's how we've defined the topology of our neural network itself. Noodle on that for a little bit. Remember, what we're setting up here is an input layer at the bottom of 784 neurons, feeding into a hidden layer of 512 neurons, which in turn feeds into our final output layer of 10 neurons, one for each classification. And we have hidden weights and biases and input weights and biases that we will learn over time. How does that learning work? Well, we need to define a loss function for that. Our loss function will be defined as cross entropy, and it's set up like this. Basically, cross entropy applies a logarithmic scale, so it penalizes incorrect classifications a lot more than ones that are kind of close, and that just allows us to converge a little bit more quickly. So digit weights will be our final output layer, so that's going to be what we're comparing against, and then the target labels are what we know to be the correct solutions, right? So we have our learned weights on the output layer, We'll be comparing that against the label data that we're training against, and we will use cross entropy to actually evaluate how far off we were. And it's also applying softmax at that stage and computing the mean across the entire training set that we have. We need to associate that with an actual gradient descent optimizer. So we will say we want to run a gradient descent optimizer on this graph within TensorFlow. Its learning rate is defined as 0.5. That's something you can experiment with. If it's too high, then you might overshoot the best value. If it's too low, you might not find it at all. And its job will be to minimize that cross entropy loss function that we just defined above. Now, before I forget, let's go ahead and run these. Starting up here, run that block, and we'll run this block to actually set up the topology of our network. Click in here and Shift-Enter to set up our loss function, and Shift-Enter in here to define our optimizer. All right, moving on. Now we also need a way of evaluating how good our model is. So to do that, we're going to set up a couple of more things. One will be something called correct prediction. Its job in TensorFlow will be to check the argmax of both the output layer and the argmax of our labels and see if they're equal or not. So basically, it's a function that says, did my prediction match the actual correct value? Yes or no, 1 or 0. And then we will compute an accuracy function that just takes the mean of that across the entire training data set. So Shift-Enter to get that set up. And now we can actually train it and see how it works. So this is where the action happens, guys. We'll start off by creating a TensorFlow session called ses. And this little bit here of config proto device count stuff, that's just a little bit of a hack to work around a bug on Windows. If you're running TensorFlow GPU on Windows, you will need that to actually avoid a crash. Otherwise, it's not really necessary. We will run our global variables initializer, and that will just associate all the initial values into our variables, all those 0 initial biases and normally distributed initial weights. Next, we're going to set up a function called nextBatch. So the way we'll go about training this neural network is to do it in batches of 100 training samples at a time. So for a given number of epochs, we will randomly select 100 training samples and do gradient descent on that. Basically run that through our neural network and use that as a step in optimizing and learning what those weights and biases should be. So all nextBatch here does is it takes our entire input data that's being provided to it, it shuffles it by random and plucks off the first however many values that we want. It then just returns the resulting image data and labels that come back from that random sample. So basically it's taking a random sample of the data that we put in. So we will actually train this over 2,000 steps or 2,000 epochs, if you will. We'll go and grab a batch of 100 random samples from our training images and training labels. We'll call that X batch and Y batch. The convention is usually to call your feature data, your images in this case X, and your labels will be called Y. Next, we will actually run our gradient descent optimizer on here with that batch of training data. So we say that we're going to actually run our session here using our gradient descent optimizer, which uses the cross entropy loss function that we defined. And we will associate the following data with the placeholders that we set up earlier, right? So remember, way back earlier on, we defined placeholders for input images and target labels. This is where we associate that batch of input images with input images and our batch of training labels with target labels. And that will actually run gradient descent on our neural network, on our TensorFlow graph, if you will, and learn a little bit more about what the best weights and biases should be along the way. For every 100 epochs, we'll print out our status along the way. We'll say that we're training whatever epoch it is and print out our accuracy as we go using that accuracy metric that we defined above. So let's go ahead and run this and see how long it takes. Off we go. Pretty quick. This just needs to get to 2,000, and you can see that the accuracy is improving over time. Initially, it started off really low, like 15%, but even with just 100 epochs, it got up to 85%, and it's just getting better and better. But you can see it started to converge there after time, right? So the incremental improvement between each batch of 100 started to get less and less, and after 2,000 epochs, you know, it's starting to get into the world of diminishing returns. That's why I chose 2,000 epochs here. Anyway, that does give us about 92% accuracy, and that's not really bad. You know, we didn't really put a whole lot of thought into how to set this thing up. And again, it's dealing with these weird 1D representations of these digits. So it's kind of impressive that it did that well, if you ask me. We can do much better, though, and we will later in the course. So let's get a feel of what these results look like. Okay, so one way to do that is to look at misclassified images and see just how tough those would have been even for a human to classify. So what this function is doing is it's going through the first 200 samples of our test data set and seeing if they're misclassified or not. And if so, it will print them out so we can examine those incorrect results. So basically we say x will run between 0 and 200 here. And for each x, we will pluck off a test image and a test label from our test data set. And we will use that as basically the training data for our neural network to actually evaluate the results. So a little bit of confusing terminology that I chose here. X-train is actually coming from our test data, and Y-train is actually coming from our test data as well. Anyway, we'll start by converting back that one hot label to an integer that we can read and call it label. We will then run our neural network on the resulting digit weights final output layer, which has already learned its best weights and biases. And we will feed in as input this time in the input images placeholder that single image, X-train. And we will call argmax on the result to get back the actual base 10 number that result represents. Once we have that result, basically what our neural network says it thinks that image represents, we can compare that to the known label, and if it does not match, we can print it out. We'll just say we predicted this number, it was actually this number, and then we can actually display the result by reshaping it back to a 28 by 28 image. So let's go ahead and run that. And we can see some examples of where it got it wrong. So for example, we thought this was a 4, it was really a 5. That is pretty tough to read there. So I really don't begrudge the system for not getting that one right. That's supposed to be a 4. Our best guess was a 6. Does not look like a 4 at all. So again, not a big surprise. We thought that 8 was a 2. That's a little bit sketchy. I mean, it is kind of a funny shaped 8. Looks a little bit upside down, but clearly there is room for improvement in our neural network here. What is that? I don't know. Apparently it was meant to be a 3. Our best guess was a 5. Not really sure how you got a 7 out of that image. So, I mean, a lot of these examples where it got it wrong, to be fair, they are examples where a human would have trouble too. Like, what is that squiggle supposed to represent? Apparently that's supposed to be a 2. We guess 7. I mean, that's not that unreasonable. But, there is room for improvement. It's still the case that a human brain can do better than what this neural network is doing, and we will examine ways of improving on this later in the course. But if you want to play around with this some more before you move on, go ahead and see if you can improve the accuracy just by playing with some of the parameters in the topology of the network. Try using more hidden neurons in the hidden layer, see what effect that has. Try using fewer. Do I really need 512? Is that too much or too little? Is the 0.5 learning rate too high or too small? Try a different one. Try adding another hidden layer in there in the middle. Try different batch sizes. There's a lot of parameters and hyperparameters you can experiment with, and often just getting the best results out of a neural network is tuning those hyperparameters. So play around with a little bit, see if you can get better results. If you can, love to hear about it. And it's a good way to learn about how this stuff works more intuitively. Anyway, we've done this all the hard way, so we've kind of like forced you to learn this at a lower level. As you'll see, there is a much easier way of doing this using a higher level API called Keras, and we'll dive into that next.